Okay, welcome back, and we're going to continue on with Chapter 4 with discussing evaluating logarithms and the change of base formula. So these are the things we're going to talk about in this video. So common logarithm just means that it's going to have a base of 10. So if it has a base of 10, we just write log x. So if you just see log x, it's assumed that the base is 10. So a calculator has that key, so it has the base log key, and it actually just says log on it. And so you can use your calculator to take the common base or the common log of any positive number. So you can use your calculator to find the values of these logs. So you could just do the log of 1,000, okay, and log of 42, and log of this number, okay. So here's what you do. So you just take log and basically just doing 1,000. So if you do log of 1,000, you get 3. Log of 142, you get this number, and log of this number, you get this number. Okay. So most common logarithms that appear in calculations are approximations. Okay, so as you can see, this is just an approximated value. So one application of logs is the pH scale. Okay, so when we look at concentration of hydrogen ions, which is what makes something acidic, so we can look at pH, right? It's the proportion of hydrogen ions. Okay, so the pH is actually on a log scale. Okay, where this is the hydronium ion concentration in moles per liter. Okay, now some of them is going to be see how it has H3O, so we're looking at positive ions, hydrogen ions that are in there. So the pH value is a measure of the acidity or alkalinity of the solution. Okay, so in other words, is it an acid or is it a base? So if it's closer to 1, it's going to be acidic. If it's closer to 14, then it's going to be a base. Okay, where a pH of 7 is neutral, so like pure water. Okay, so we're going to round to the nearest tenth, which is the customary thing to do for pH. So now, if we have a concentration, so these bars mean concentration, so usually moles per liter. Okay, so the concentration of the hydronium ion is this. Okay, and so we want to find the pH of a solution that has this concentration of ions. So we use the pH as the negative log of that concentration. And so we take the negative log of this, and so now here we're using the fact that this is 2.5 times 10 to the negative fourth power, so we can use the property of logs that can break this down into a sum. So we can take the log of 2.5 plus the log of 10 to the negative fourth. And so then we get this minus this, and we take the opposite of that, and we get a pH of approximately 3.6. Now, in this case here, we want to find the concentration, and we're given a pH of 7.1. So now what we're going to do is we're going to use the same equation, but now we know the pH, and we want to solve for this one. So we get 7.1 is equal to the negative log of this concentration, right? And so we multiply both sides by negative, and now we got the log, right? So what are we going to do with this log? Well, now we're going to raise both sides to 10 as a power of 10, because we're going to use the property that when we go 10 to the log base 10, it's going to cancel each other out, and we're going to get the argument out. And so we get the concentration of hydronium ions is equal to 10 to the negative 7.1 power. And of course, we can approximate that as 7.9 times 10 to the negative 8. Okay. So note, in the fourth line of the solution in this example 2a, we use the equality symbol rather than the approximation symbol when replacing log 2.5 with this. Okay, this is often done for convenience, despite the fact that most logarithms in applications are indeed approximations. Okay, so it's more or less just for convenience. When we deal with applications, it's usually always an approximation. Here's another one. says wetlands are classified as bogs, fens, marshes, and swamps based on pH values. A pH value between 6 and 7.5 indicates that the wetland is a rich fen. When the pH is between 3 and 6, it is a poor fen. And if the pH falls below 3 or less, the wetland is called a bog. Okay, so the more acidic the water or the soil or the pH of the environment is, the more it is categorized by that. So it says, suppose that the hydronium ion concentration of a sample of water from a wetland is 6.3 times 10 to the negative fifth power. How would this be classified? So the first thing we need to do is find the pH, and then based on this scale or these categories, we're going to figure out which one it falls into. So we want to find the pH. So we've got the concentration, so let's use the formula. So we're going to take the negative log of this, so we're going to split it up into the log of 6.3 and the log of 10 to the negative fifth power. And so this is going to give us negative 5. And we're going to take the negative log of 6.3 minus, because we distribute the negative sign, of negative 5. So negative log of 6.3 plus 5. And so we get approximately 4.2. Okay, so now based on that 4.2, this would be categorized as a poor fen. Okay. Now what about loudness? So this is where decibels come in. So the loudness of the sounds that we hear from the human ear is measured in decibels. We first assign the intensity of the initial intensity, which is the smallest sound or the softest sound that can be heard by the human ear. Okay, so this is what we call the very faint threshold sound. And so that's measured by the smallest, or not the smallest, the softest sound that can be picked up by the human ear. And so then what we're going to do is we're going to, if a particular sound has an intensity I, then the decibel rating is given by this log equation. So we take the proportion of the intensity of the sound divided by the reference sound, the base sound, I naught. Okay, so we're going to take 10 times the log of that ratio, and that's going to be the decibel reading. Okay, now we want to find the decibel rating D of a sound with an intensity 10,000 times that of the base sound, the reference sound. Okay, so we're going to replace this. We're going to substitute this in for I. So we're going to replace it with I, and so these two cancel each other, and we're going to get the 10 times the log of 10,000. And then this is going to give us 4. So then we get 4 times 10, which is 40. And so the decibel reading is 40 decibels on the scale. Now, natural logarithms. So now we're going to talk about the natural logarithm, ln. So in most practical applications, we're going to use the log base e, which we're going to call the natural logarithm, because it occurs in many of the life sciences, economics, and other growth and decay situations. So we're going to use the base e logarithm, and we're going to use the symbol ln of x. Okay? The expression ln of x represents the exponent to which we must raise e in order to obtain x. Okay? So that's why we call it the natural log. So now, the natural log, for all positive numbers x, the natural log is the log base e of x. So there's the definition. And again, we have an ln key on our calculator. So using our calculator, we can calculate any one of these. So this one's going to be 3. And then, of course, these, we're going to have to use our calculator to get an approximate value. Okay. And so we can see from our calculator, you can use the ln key and just plug in 142, and it'll give you this value. And you can plug in this number in to the log, and it'll give you this value. Okay, and again, these are approximations. Okay, now measuring the age of a rock, geologists sometimes measure the age of a rock by using atomic clocks. Okay, by measuring the amount of potassium 40 and argon 40 in a rock, it is possible to find the age T of a specimen in years with this formula. Notice that this involves the natural log here and here. and the ratio of the amount of argon and potassium 40, argon 40 and potassium 40. Okay, so now let's use this formula, and it says how old is a rock in which the argon is 0 and K is positive. Okay, so that's what we're going to do. We're going to say A is 0, so this is going to be 0. So this simplifies to this. Okay, so we're going to use this is 0. So that means that this is just going to be the natural log of 1 over the natural log of 2. And then we're going to take this. So we can plug these in our calculator very easily. And so this gives us 0, 0, so time is 0. Okay, so because natural log of 1 is 0, right? So this whole thing is going to be 0. So we get t is equal to 0. So the rock is new, right? So it's not a very old rock at all. Now, what if we get a ratio, the ratio for a sample of granite from New Hampshire is 0.212. So we get the ratio. We find the ratio of this sample is 0.212. How old is the sample? So now that we know the ratio, we can plug that into our formula. And so now we get the natural log of this divided by the natural log of 2 times this. And we get 1.85 times 10 to the 9th power. So how old is this rock? About 1.85 billion years old. Now, what about modeling global temperature increase? Well, carbon dioxide in the atmosphere traps heat from the sun, and the additional solar radiation trapped by the carbon dioxide is called radioactive forcing. It is measured in watts per square meter. In 1896, the Swedish scientist Svante Arrhenius modeled radiative forcing R caused by additional atmospheric carbon dioxide using this logarithmic equation, where the C0 is the pre-industrial amount of carbon dioxide, C is the current carbon dioxide level, and K is a constant. Arrhenius determined that K is between 10 and 16 when C is double the initial value of carbon dioxide, the pre-industrial level. Let C equal to C0 in the relationship between R and K linear, let C equal 2 times C0 is the relationship between R and K linear or logarithmic. Okay, linear or logarithmic. Let's find out. If C is equal to 2 times this, then C divided by C0 is 2. So R equals K times the natural log of 2 is a linear relationship. So now it becomes a linear relationship because now we just got a constant here. Okay. Now B, the average global temperature increase is given by T of R equals 1.03 R. So we want to write T as a function of K. Well, we can put R in, right? We can plug in what the formula for R is. So we start with this, and we plug in R. R is equal to this. Okay, the given expression R is K times the natural log of C over C0. Okay, so now what do? We want a function of K. Let's see here, where these are going to be known. Okay, that's it. So this is our function of K. Now, we can also use our calculator to find values of either natural logs or common logs. However, sometimes we need to use logs that have other bases. So we're going to have to use the change of base formula, which comes from the change of base theorem, so that we can change any log of any base to either a common log or a natural log, or any other log actually. So the change of base theorem says that for any positive real number x, A and B, where A and B are not equal to 1, the following relationship or equation will hold. We can take log base A of x, okay? We could take some other log base B, doesn't matter what it is, and as long as we take that log of the argument divided by that log of the base, we're going to be able to calculate what this is. So we could take any log of any base, and we can basically write it as a ratio of another log of a different base, as long as the top is the log of the argument divided by the log of the base, or the old base, I guess I should say. So let's say we have this log base 5 of 17. And we want to approximate it to 4 decimal places, and we want to find the answer. Okay, so what we can do is we can use the change of base formula, right? And let's use natural logs. It doesn't matter what logs we choose. We could use common logs. You'll get the exact same answer. So let's use natural logs. So we're going to say the natural log of 17 divided by the natural log of 5. And then we can plug this in our calculator easily, and we get approximately 1.7604. Now what about this one? We could do the same thing here, right? Now we have log base 2. Let's rewrite this using common logs now. So all we do is take the log of 0.1 divided by the log of 2, and we get negative 3.3219. Okay. Now, modeling diversity of species. So one measure of the diversity of species in an ecological community is modeled by this formula. H is equal to the negative of the sum of these logs, where you have P1, population 1, times the log base 2 of population 1, plus population 2 size, times the log of base 2 of the population size of population 2, all the way to the nth population. Okay? So where P1 through Pn are the proportions of a sample that belong to each of the n species found in the sample. So P1 is the proportion of the species, how do I say this? It's the proportion of species 1 of the sample. So what proportion of the sample belongs to species 1? What proportion of the sample belongs to species 2, and so on and so forth. So that all of the proportions should add up to 1. Okay? It says find the measure of diversity in a community with 2 species where there are 90 of one species and 10 of the other. Okay, in other words, 90% of the sample is of one species and 10% is of the other. Okay, in other words. So since there's 100 members in the community, we can do 90 over 100 is P1, so 0.9, there's your 90%, and then 10% or 0.1 for P2. And then now we can say H is equal to the negative of 0.9 times log base 2 of 0.9 plus 0.1 times log base 2 of 0.1. So now, in this case, we can use, from the last example, we can find that log base 2 of 0.1 was approximately negative 3.32. Okay? And then for this one here, we can use the change of base formula and say the log of base of 0.9 over log base 2 is equal to negative 0.152. So if we add both of these together, we get negative what? 3.472. And then you take the opposite of it, and you get positive 469. So verify that this is approximately 0.971, right? If there are 60, so verify that H is 0.971 if there are 60 of one species and 40 of the other. As the proportion of n species gets closer to 1 over n each, the measure of diversity increases to a maximum of log base 2 of n. Okay, so this is H. Okay, if there are 60 of one species and 40 of the other. Okay? As the proportion of n species gets closer to 1 over n each, the measure of diversity increases to a maximum of natural log of base 2 of n. Or not the natural log, I'm sorry. I'm sorry, not the natural log, but log base 2 of n. Okay, so that ends this section. And again, if you have any questions, please let me know. If you want me to work out any problems in class, email me or just tell me in class. We can work through those together. And just make sure you practice, and go through the examples. Not only the examples here, make sure you know how to do these, but also some of the other ones that are found in the textbook. And also do some of the exercise problems at the end of the chapter for extra practice. And if you get stuck on any of those or the homework problems, by all means, email them to me or let me know, and I'll go over those in class. Until then, have a great day.